All right. Hello, everyone. Welcome to our Journal of Mechanical Design webinar. My name is Carolyn C. Prasad. I'm the editor-in-chief. And I just want to do a couple of introductions before we get started. Wanted to thank Amy Susky, our assistant, and Faez Ahmed for all of their assistance in organizing this behind the scenes. And a huge thanks to Alison Olechowski, Tucker, Marion, and Mohsen Moghaddam, who organized this session. So we're really looking forward to the speakers today. It's wonderful to see some familiar faces and some new faces out there. And so I will turn it over to Alison to get started, and she will introduce the first speaker.
Great. Thank you, Carolyn. So before we get to introducing the first speaker, I just want to set the stage a little bit here today. So this is the 9th JMD webinar, and the topic is Emerging Technologies and Methods for Early Stage Product Design and Development, which is in fact a recent special issue in the journal. I just want to echo what Carolyn said, which is to highlight the fact that today this webinar is hosted by myself and Mohsen and Tucker, so you'll see the three of us pop up to introduce our speakers, but that we had three other guest editors or associate editors working with us on this special issue. So that's Chris McComb, Kate Fu, and Katja Holta-Otto. Again, I just want to echo the fact that we couldn't do this. We're really excited to have this webinar and to hear from these speakers. So thank you, Faez, for helping us organize. Thank you, Carolyn, and also thank you, Wei, and it's great to see you, Wei, as the editor who helped us make it through this process. And of course, thank you, Amy, who keeps us organized and make sure that we're doing what we're doing. So I'll just give you a rundown of the way it's going to work today. We're actually going to hear from our speakers and have the opportunity to ask them questions right after their presentations. We'll follow that up though at the end with a full discussion, maybe a more open discussion that relates all of the papers. Perhaps if you have sort of a forward-looking question, for example, we'd love to hear that at the end. And if the conversation goes forward and you connect with someone that you'd want to continue talking with, Faez will be sharing a link to a GatherTown, so another virtual platform for collaboration that we're all welcome to move to at the end of the seminar to keep the conversations going. So you probably know this already because you're here for the webinar, but just to highlight this, we have a great set of papers in volume 145, issue 4 for this special issue. We also have an editorial that ties together this theme. And so the purpose of our article, and of our special issue in general is to synthesize the state of the art on research methods and new technologies for early stage product design and development. And so technologies like artificial intelligence or virtual and augmented reality, or cloud computing, for example, have the potential to really augment the performance of designers in the design process. And so in our editorial, we've framed the 16 papers that make up our special issues under 3 themes of product design and development, as well as a 4th theme, which is the evolving role of designers in early stage product design and development. So we think there are 3 major ways, three major tasks that happen in the early stage of the PDD process: problem exploration, concept generation, and concept evaluation. And today we'll be lucky to hear from our 4 papers that sort of highlight each of these 3 different activities. So with that, I'm going to actually pass it over to Mohsen, who will introduce our first speaker.
Well, thank you, Alison. Thank you, Carolyn, for the introduction. The first speaker is Jonatan, Martin, Escorcia-Hernandez, who will be presenting their first paper on behalf of his co-authors, Matthew Gorsard and Florian Gosselin. The paper is entitled Task-Oriented Methodology Combining Human Manual Gestures and Robotic Grasp Stability Analysis Application to the Specification of Texas Robotic Grippers. And this is related to the first area that Alison mentioned. Without further ado, Jonatan, over to you. And yes, you have 13 minutes. Right, go ahead.
Okay. Well, thank you very much for this introduction, Mohsen. So let me share my screen. Okay. Everyone can see my presentation?
Yes.
Okay, so this is my paper, text-oriented methodology, combining human manual gestures and robotic grasp stability analysis for the specification of the extruded robotics grippers. This is the outline of my presentation. First, the context, problem formulation of this presentation, in which consists the methodology that we propose, then the different steps that conform this methodology, that is a human-centered gesture analysis, force-based graph stability analysis, then the obtained results, and finally the conclusions. So then the problem, the context and problem formulation. Robotics currently are intended to be integrated more in environment for humans, human recurrence environment, we can say. And to perform this kind of activities, we need to design a crucial device, that is the gripper, or in most of the cases, a robotic anthropomorphic gripper or hand. And we can say that the most apparently easy solution is to develop a device that exactly replicates the kinematic of the human hand. But even if this has some advantages, the inclusion of anthropomorphic device, 100% anthropomorphic devices, in several cases, they have some drawbacks as highly complex mechanics. They require a large number of actuators, and sometimes the dexterity is not always warranted. So the purpose of this paper is, okay, based on a certain task, a certain activity that we want to optimize, how can we establish or define the parameters that the future gripper or future device must to accomplish? So in some studies, it's saying that for center activities, the human beings tend to use a reduced number of rows, and taking this into consideration, we can define some strategies to answer some questions that are related to the design of the device. So what is the optimum number of fingers that the device needs to perform a specific activity, the dimensions, how many degrees of freedom, where to place the tactile sensors in this case, and what is the amount of force that the gripper, the device, must provide to perform a specific procedure. So our methodology consists in the following steps. First, we select a use case, and from this use case, we see the videos of the use case. I'm going to explain in this case what is the use case that we choose for this work. First, we identify the manual patterns. We identify the contact areas between the object and the hand. Then with this information is complemented with the identification of the time in which each grasp pattern is used. We also identify the direction in which the human hand applied the force. And this information is used to generate interaction maps. With all of this information, we have solid guidelines to define some specifications as the number of fingers, degrees of freedom, and the best place to place data sensors. Then the next part of the analysis is theoretical analytic analysis that consists in a force graph stability analysis in which we make use of software, a CAD representation of the use case object. Then taking into account the graph pattern, we assign the different contact points. We establish the applied forces or disturbance into the task in order to compute the required level of effort needed to counterbalance such disturbance. Then we generate a graph in which all the data it's analyzed to take a decision to define the specification regarding to the actuation system. So this part of the use case it makes a part of a project called TriSpot, in which we are interested to develop a gripper to perform the sterility testing. Sorry, and it's necessary to develop a gripper that keeps a high degree of dexterity, but with simpler kinematics. So from these videos, we first analyze a graph pattern. From this graph pattern, we select a classification from the classification of the existing literature. And due to that, there are several graph patterns that are not classified in the literature. We develop also a new, we complement with a new taxonomy. Then, taking into consideration such graph pattern, we define the regions in which the object is in contact with the object. Due to that, for this use case, the operator use globes with also replicate the grasp in order to have a better appreciation of the involved contact surfaces. So here are the all identified graph taxonomies of the use case, and then we generate a table in which we register the beginning and the end of each grasp, and also we put inside other information. For instance, if the task was performed with the left hand, with the right hand, and this information is useful to identify which grasp, what are the graphs that are more frequently used. Then, by carefully visual inspection, we identify the direction in which the exerted force, the direction of in which the exerted force it's made. So for each elementary contact area, we define a frame, and all of this information is combined, is merged in order to generate the interaction maps. These interaction maps are useful to take some decisions regarding the kinematics of the fuller fingers based on the frequency of use of the whole use case by each elementary contact area. In this case, mostly of the tasks are solicit the C direction, and the thumb is the mostly used finger. So with this information, the next part is the force graph stability analysis. In this case, we use graph theory, and the objective is to by combining the different set between object, hand, contact points, and several applied forces, is to know, okay, what is the magnitude necessary to counterbalance an external force in order to define the specification of the future actuation system. So, as previously mentioned, first we make a collection of the object CAD model objects. These objects are associated to several graph patterns, and we associate this graph pattern to the object virtually. We construct a meshed representation of the object, the contact points, and we make this for the whole combination of the use case. Then, by using the quality metric, we put the external disturbations that we compute. We measure experimentally, and the results are shown as follows. I'm going to put in detail an example. For instance, this task, that is needle on cap phase. First, we identify the surface in which that are in contact. We associate virtually to the object. We identify with respect to the center of mass. With respect to the object frame, the position of the contact points. We associate the perturbation. In this case, needle on cap task was estimated as in the vector that is shown in the screen. This information is used to solve the optimization problem. And then we compute the force, the contact force, but we are interested to work purely with the normal contact forces. And we select, taking into account these criteria, the criteria of the maximum effort, of the maximum normal contact effort. We say that in order to perform this task, it's necessary that the gripper, each of the fingers, should provide at least 16.6 newtons. We perform this process for the whole combination between object and grasp, and in this case we are arrived to the following specifications. In this case, taking into account the results of the human gesture grasp analysis, we say that a 4-finger configuration is enough to this to perform this use case. Each finger, due to that, was performed based on a human-based observation, should contain three phalanges. The tactile sensors should be incorporated at each of the 3 phalanges. And in the case of the actuation system, each finger should provide at least 20 Newton, sorry. We generate a previous suggested configuration in which was used for to grasp the use case, but it's a preliminary kinematic configuration of the gripper, and for sure it's necessary to make some optimization later. So conclusions. We propose a new methodology for the specification, technical specification of multi-finger grippers. This methodology was used to define the specification of a gripper dedicated for the sterility testing process. In structure, the first part of the analysis is useful to define the structure of the gripper, whereas the second helps to establish the force capability of the device. A 4 kinematic configuration with 3 human-like phalanges, it's suitable to accomplish the task of the mentioned use case. It was defined that each finger must provide 20 Newton at least at the fingertip, and tactile sensors should be incorporated in the 3 phalanges of each finger, the palmar side, in the future palm. So also I would like to thanks to my colleagues, Matthew Grosser and Florian Goslo. Thank you very much for your attention.
Oh, Alison, I'm not sure if you or Tucker will be introducing the next speaker.
Thank you, Mohsen. It's my pleasure to introduce the next author of the paper, Jana Saadi. And she is currently a doctoral candidate at MIT and in the ideation lab. And she's working on very interesting research on generative design and its impact on the concept development process. And that's what the paper is on. Her co-author is Professor Maria Yang. And the paper is entitled Generative Design, Reframing the Role of the Designer in Early Stage Design Process. And it's an interesting qualitative study into how designers are actually using tools such as Fusion 360. I'm very much looking forward to your presentation.
Thank you, Tucker. I'm just gonna start sharing my screen here. All right, yes, so I'll be presenting today on our paper regarding the generative design process and exploring the role of the designers and generative design tools in this process. So generative design tools are tools that are driven by AI algorithms. They use designer set inputs to generate a large number of design outputs. And these generative design tools have really been increasing in use, both in research and in industry applications. So an example of that, how it could be used is shown here. So this is an engine bracket that a GE engine bracket that has been optimized to minimize the weight while maintaining an appropriate stiffness. So I think this one's 40% lighter and 20% stronger, the optimized version compared to the original version. And this was done using Fusion 360's generative design tools. So generative design, designers have this opportunity to use generative design tools to create products or designs that are more complex than what they can create on their own. But really not a lot of research has been done to fully understand this extent that these tools can influence the design process and the design outcomes. Previous research has shown that design tools in general can influence the way designers approach processes, and computational tools have this potential to influence design outcomes. So this really illustrates that what you use to design and your process to design does matter. And so our paper seeks to understand more about this generative design process and what influence generative design tools can have. There have been some suggestions for what this generative design process may look like and how it could differ from a more traditional process. But these processes tend to be oversimplified, and they focus on the role of the tool and don't really outline the role of the designer and this interaction between the designer and the tool. And so our goal for our research is to map out a more descriptive process and understanding all the factors that go into it. And so this research looks to develop this fundamental understanding of the interaction of human designers and generative design tools to understand this generative design process through these research questions. And we investigate these research questions using a grounded theory approach, which allows for this development of theory that's rooted in qualitative data. So we conducted 6 unstructured interviews with designers that use commercially available generative design tools. And these interviews were then coded and thematized to develop this generative design process. And the designers that were interviewed used a variety of different generative design tools that were based in many different commercial CAD softwares, including CATIA, Grasshopper, Entopology, and Fusion 360. And this is really just a sampling of where generative design tools might exist. So the way we did the coding process is first, we had transcriptions for the interviews, and using qualitative coding methods, we had about 150 codes that were ended up being created. And we did this through several different levels. So the first would be an open coding process, which summarized the theme of the passage, which is just to focus on the meaning of the statement. So for example, a statement of saying we quickly calculated that was coded to mean using like back of the envelope calculations. Then we used an axial coding method to organize the themes into broader categories. So for example, the calculations and loading approximations were thematized to mean estimations. And then finally, a theoretical coding was used to refine the groups and thematize the categories, and then link all the categories and subcategories to create this overall process. So the estimations really were an indication of intuition that was used in the setup process, and that was all in setting up the constraints. And we kept doing that over and over until all of the codes were generated, and we were able to derive a process. So that process I'll present right now. So these first, the designers would identify the objectives, parameters, and constraints that they want to input into the generative design tool. So these can be very different depending on the product, the process, and the tool. But for example, some objectives could be like minimizing the weight or maximizing thermal efficiency. And often designers will use their expertise and their intuition to identify what these inputs might be. So as one interviewee had said, that this is where all their past experiences can tell you, and the knowledge and physics of the behavior of the elements can define what the variables should be. Next, the generative design tool will output several designs, which are then evaluated by the designer. And the evaluation is done both qualitatively and quantitatively. So the performance, how does the design perform in terms of the objectives that were specified, but also things like, how does it look? Does it look like as I expected? And the designer will keep on iterating and looping through these objectives, parameters, and constraints as inputs to the tool. And often these first few rounds of iteration are focused on more of the quantitative evaluation, so ensuring that all of the parameters and constraints are accounted for. And then the iteration starts to become a bit more qualitative and focusing on how things look. For example, as one designer had said, that they wanted to use these generative design tools to show off the technologies they're incorporating. And so they wanted something that looked really, really cool. And so they kept on making sure that it looked like that it was made using generative design. And so they spent a lot of time iterating and fine tuning on those parameters to make sure it looked the way that they wanted it to look. After the tool generates a set of outputs that the designer is satisfied with, they'll select from the designs and then further refine. And here again, the designer will use their expertise to select. So as one interviewee had said, that you can even select something that's less efficient, but you know that maybe it's better, easier to manufacture. So, and they know that based off of their personal experience. So they're going to choose this more optimal in terms of manufacturing, as opposed to the more idealized version of the product that was created using the generative design tool. So really putting in their own expertise and their own intuition into the selection and refinement stage. And then another important output of this process is understanding of the design space. So really, what are the constraints and parameters? How do they influence the design, and what the extent of the solution space might be? So as one interviewee had said, for them, it's a learning experience, and it helps them gain confidence in what they're doing and understanding the problem. So even if they get early on some results that they like, they still want to take the time to understand what's going on. So it's a bit of a trial and error iteration that helps them build this understanding of what the problem space is and what the potential solution space might look like. And from the interviews, we learned that designers considered three main factors throughout the different stages of the process: quantitative performances, such as the objectives, the qualitative performances, such as aesthetics or how it relates to users in the context, and then also manufacturing, design for manufacturing and design for assembly considerations. And they considered these through different methods, like using their expertise, so their intuition, experience, and knowledge, and inputting these factors. They also might do some visual evaluation to evaluate the designs for quick feedback. And then they some calculations or prototyping for more thorough considerations. So there are several implications of the generative design process that we derived from the interviews. First is that using these generative design tools, as you can kind of tell, it's very constraint-driven process. Instead of thinking about how the shape of an object should look like, designers are thinking about what the constraints the shape and everything that has to be around the shape. So as one designer had said, you need to be able to abstract your goals. So you have to know where your connection points are, what your loads are, where it needs to be constrained, how you have to access those things, so design for manufacturing and assembly considerations. The process, this constraint-driven process can also bring about a different type of creativity. So designers have to be more creative in how they use the parameters and constraints as inputs to the tool to really try to influence the shape of the product that gets created. And this is especially true for features that cannot be controlled directly by the tool, such as, and in often cases, aesthetics. So as this interview had said, you can start predicting the types of geometries that you're going to get out of the tool. And so you'll start using clever load cases to be able, and the way you might insert obstacle geometries to be able to manipulate the actual shape of the outputs from the generative design tool. And this generative design process can also give a high potential for learning about the design process and the solution space, especially early on in the design. So as one interview had said, you'll get a sense of the geometric considerations and how they're going to impact aesthetics. So you'll see in some outputs of the tool, you'll have like very dominant lines, or there's very clear, thick geometries in places. And you can intuit that that means that there's lots of load that's being transferred there. And you'll have some subdominant lines that are really just reinforcing that. But that helps give an understanding of where the design constraints might be. And I think all these implications are quite interesting, and they should be investigated further to understand this extent that they can have and their effects on the design process and design outcomes. So just to motivate that a little further, the interviews that indicated the emphasis on constraints, which are often quantitative in nature, can make it difficult to incorporate more qualitative aspects. So as one designer had said, when you're thinking about optimization and the very technical parts, it can be easy to lose this track of community and look at something that's not doable. So for example, this geometry they were creating, which was best performance in terms of the objectives for a certain location, they know that it's very hard to build. So there's some manufacturing considerations related to the context. And also every time they've shown the geometry to people in that context, they'll say that it looks very narrow, or they'll be scared of using that product. And in their case, and often many design cases, you're making an object that will interact with people every day. So it has to be something that you can evaluate from a design perspective, which I would say is like the quantitative objectives, and from more of an experiential point of view, so more qualitative objectives. So this effect that the constraint-driven process has on balancing the qualitative and quantitative aspects should be further investigated, and how we can maintain this human-centered design process while using these generative design tools. We also saw that designers can also begin to use this generative design tool in very creative ways and mixing it with more traditional design processes. So for instance, this generative design tool can be used just to gain an understanding of what the parameters and constraints might be and how it can influence the design. And then it can be used after that to be a source of inspiration or a starting point that can be used in more traditional design processes, which is what this designer had said. They really start using the generative design tool to create something that they thought was okay in terms of FEA and the shape. And then they stop using the design tool and really go to a more traditional design process, starting off with what was created with the generative design tool. So really the possibilities of using these generative design tools on idea generation, and should be further research to understand the applications and the capabilities of inputting these tools in the design process. And finally, the learning aspect of the generative design tool, I think, is rather interesting. As one designer had said, they found a very interesting takeaway from using the generative design tool, because they drew the geometry in a very certain way, thinking that from a thermal radiation point of view, it makes sense. But then they found that a lot of the optimal surfaces that were generated by the tool were actually drawn geometry in reverse. And the reason for that was this obstacle geometry that they had that was really driving the structural performance. So the design wanted to get thin in certain areas, but it couldn't because of the constraints. So it was very interesting to have your own understanding of how things might be, but then the generative design tool shows you that that's actually not the reality, and the designs that are generated are quite different. And so really, how can we use these generative design tools to learn more about the design problems? And does this better understanding of the constraints and their influence on the design yield to different design outcomes? So really, these research questions that we set out to investigate were answered through the interviews of designers using generative design tools, and the qualitative methods were used to outline a generative design process that includes both explicit and implicit inputs and outputs. We were also able to understand better the factors that designers considered at each stage and the methods in which they were considered by the designers. And then finally, the implications of the generative design tools, including the constraint-driven design, creativity on the design process, and learning in early stages of design. And all of this should hopefully give a better understanding of what the implications of using generative design tools are on the way we design things, and motivate some for future research to further our understanding of what these generative design tools are capable of and how we can best incorporate them and use them as designers. And with that, I thank you all for your attention, and I'm happy to take any questions.
Excellent. Thank you. That was really, really interesting, Jana. And there's a lot of questions in the chat if you want to answer them in the chat, or hang around and we'll try to get back to them in the discussion that we have at the end of all the papers. Before I do introduce the next talk, I just wanted to highlight that if you're enjoying this, which I hope you are, you can continue this conversation with us at a workshop at the IDETC CIE conference in Boston. So Sunday, August 20th, mark your calendars, from 1 to 4 p.m. We'll have a workshop. Tucker, Mohsen, and the other associate and guest editors from this special edition are hosting this on the same topic. We'll have academic and industry speakers and opportunities to learn about technology and methods, with ultimately the goal of launching new collaborations with these state-of-the-art technologies. So keep your eye peeled on LinkedIn and other mailing lists to see how to sign up for that, and we hope to see you there to continue this conversation. Now, I'd like to introduce our next speaker. So that is Chenxi Yuan from, or I guess formerly from, Northeastern University. And I should mention that this paper is co-authored with Tucker and Mohsen, who you know from this webinar. This is a paper that I nominated to be part of the webinar. And so Chenxi, the lead author, I'll introduce her. She received her PhD from the Department of Industrial Engineering at Northeastern University in 2022. Her research focused on developing new insights and knowledge of cutting-edge AI frameworks and methods for enhancing designers' creativity with deep neural network architectures for user-centric design, concept development, and assessment. That's what we'll hear about today. Now she's a postdoc at the University of Pennsylvania, working on developing new deep learning methodology for an advanced scientific understanding of risk factors for Alzheimer's disease and early diagnosis. So Chenxi, please, the floor is yours.
Thank you for introduction. I'm glad to be here and present my PhD work, working with my advisor, Professor Moghaddam, and Professor Marion as one of my defense committee member. So yeah, let's get started. Okay, so today I will present one of my work. The name is DD again, integrating a data-driven design evaluator into generative adversarial networks for desirable and diverse concept generation. So for the product development process, the generation of innovative, diverse, and user-centered design concept is a very important step in the early stage. And in addition, that generating a large set of concepts can also promote the creativity and also logically can allow the selection of better ideas from a large set. So both of the way have potential to leave a significant impact on the quality and success of the design for the product development process. However, there are several limitations noticed in this area. For example, the designer's tendency to adhere to a specific mental set and heavy emotional investment to really limit their creativity and innovation in the design concept generation. Also, the subjective judgment and expertise of designers sometimes may lead to the biased or inconsistent outcomes in design concept evaluation. So in the product development process, once the product is built and released, leveraging feedback from users to redesign and revise the product may be costly and time-consuming. So given on these limitations, I think there is an urge to have a significant way to augment designers' performance through the design automation. So for the design automation, we noticed there are a lot of AI research have made a remarkable progress in generating the design ideas. Here you see are 3 examples from the published paper. By using some like AI models, they generate, for example, the aircraft models, design the 2D wheel design, and also some clothes generation suggestions. So we see AI can be an inspiration tool in the creative process and being a generative tool to assist the designer in developing the design concepts. Also, it can like augment the designer's ability to create concepts faster and more efficiently due to its like a strong computer ability. AI can also analyze a large amount of data and suggest design adjustments, so designers can thus choose and approve adjustment based on this data. So among a lot of AI models, there is one model which have tremendous success in generating designs. It's called generative adversarial networks, so we call it GANs. So GANs have showing state-of-the-art performance, like in a variety generative design tasks. They range from topology optimization to material design and shape parameterization. So for people who are not very familiar about GAN, there are a little bit introduction of GAN. I just try to want to describe as simple as possible for help you to understand the GAN. So GAN is implemented by using 2 stochastic neural networks. One is generator and then another is discriminator. Generator try to generate new samples from random noise. On the contrary, discriminator classifies those generated data and try to distinguish those samples from the real images. So those 2 neural networks, generator and discriminator, they are trained adversarially to fool each other. So in this process, both models like become better at their respective tasks. So we see like GAN, by using the adversarial training, the GAN can learn the probability distribution of an existing data set to generate realistic new feasible samples. So this is about the GAN. And since GAN have like very successful performance on generating the samples, right? So we are starting thinking about like how can we use GAN to generate the new product designs. So our first work like develop an attribute of well GAN, which can like leverage GAN model to generate new product with desired visual attributes. See, like we have like existing images of the product, and our model can generate like new images with specific attributes you want. So if you look at this figure, a model can generate different color of the top and also the different length of the sleeve and also different graphic features on your t-shirt. So this is this model started a work that show us the performance of the GAN model on generating a large set of image ideas or design concepts. However, when we did this work, we evaluate our results on using commonly used computer vision metrics such as FID to assess the to evaluate the quality of generated image. However, in practice, we really want to know if this generated image or generated concepts is really needed or lacked by users. So we come up our second work that is data-driven design evaluation model to evaluate our generated products images. So this model integrates an analysis on the concept images and the text description. So because we include text description here, because in practice, we not only have the images, we also have the detailed description of the products, right? So we so that's why we develop this multi-modal evaluation model. So we leverage an image model and a text model to consider and leverage the user's information, the text information. And in addition, we also include the user review, a large size of the user review online. A language model were used here to analyze the text review into rating scores, like you see in the red set. So we use this analyze the rating score as a label of the whole model. So this model were trained to predict this rating scores when you've given any images or description of the new generated products. So in this way, this model can enable the accurate and scalable prediction of the performance rating of your generated concepts from users' perspective. And our next work use a state-of-the-art model called StyleGAN. We evaluate StyleGAN on a large-scale data set of the footwear products. We want to see how StyleGAN works on the large data sets. So as you can see the left figure, this is our generated results by using the StyleGAN. There were out different type of the sneakers. So we can see the model can generate realistic samples, right? They have the high quality and the greater appearance. However, if you looked carefully on those sneakers, you can see they're remarkably similar to the authentic products, like existing products, right? You might see they are familiar with some sneaker you might see before. So these results may not benefit designers or promote their creativity because those generated samples are neither novel nor aligned with the user need, right? So based on this, existing preliminary research results and the problem we observed, we developed DDE-GAN, try to solve the problem I mentioned before. So as I talked DDE model, which is an evaluation system before in the last two slides. So since DDE model can predict user sentiments, right, for design concepts, can only based on these images or description or both of image and description. So we are thinking, why don't we use DDE model as a tool to evaluate the generated samples during the training process? So in this work, we include the DDE model in the StyleGAN models. So we integrate the DDE model as an additional loss into the GAN's discriminator. So you can see, you can understand it as when you generate a new design concept, right? We usually generate a lot of steps, or the model generates the image intuitively for several iterations. By including the DDE loss, it evaluates the every time it evaluates the generated samples and give you a rating scores, and these rating scores can serve as a like feedback or like assessment value back to the generator, and allow your generator to adjust your next step for generating a new round of concepts. So since DDE measures the intermediate samples generated by the generator in each iteration, and it conveys the loss back to the generator for new set of parameters. So our proposed DDE GAN model is expected to generate the better designs, not only with the high quality, but also from the user's point of view, say like can also meet the user's requirements on the products. So here, let's go to the qualitative results of our DDE GAN model. First, I would like, before we see the results of DDE GAN model, I would like to show the baseline model results. So these Sneaker samples you're looking right now are generated by using the style GAN. So these samples, they emphasize a high quality, of course, and you can see there, like we can generate a tremendous set of like images, like serving as the design ideas at the same time at a very short time. But one big problem is these images are similar to existing products, right? If you look at these sneakers, you can see they have some shared features such as from Adidas or Asics or Puma. So, however, compared with the style GAN, those samples are generated by our DDE GAN model. So since like when we did this project, there is no like diversity criteria were defined. So in this paper, we self-designed the attributes such as strange or you never seen before as a criteria to identify if your samples are diverse or not. So if you look at this figures, which contains like 86 or 84 images, so we see some like we see a high quality results, but also we can see several sneakers. They are kind of novel. And let's see a more detailed of examples. Here are like 14 examples I just manually picked up from the last figures. So those example of the sneaker, they have high diversity observed, right? You can see some, they are like kind of have kind of novelty and you may not see before. So these sneakers are far from the similar, like we mentioned before, to the existing sneakers. They look distinguishable with more novelty and diversity. So yeah, that's about the qualitative results. So we still need to further assess our model, DDE GAN model. So we conducted a quality test. Here we use a commonly used like matrix called Frechet Inception Distance FID. This matrix is used to assess the quality and diversity of synthetic images because it compares the distribution of the generated and the real images. So usually a lower FID score indicates a closer distribution. That means a lower differences. So that means a better performance of the generative model. So let's look at the results here. We see style GAN has and DDE GAN, they both have a pretty small FID scores. So it is interesting to mention here that it is commonly acknowledged that FID score below 10 is sufficient to demonstrate the effective generative model. So which means that both style GAN and DDE GAN with a lower FID represent their higher performance of generating the high quality images. As I believe you have saw the images I showed before, they have really, really high quality and resolution. However, since I said the lower FID, because the FID, they calculate the differences between objective images and the generated images. So lower FID, they indicate a higher similarity. That on the contrary, that means the higher FID, right? They indicate the lower similarity. So here we can see the DDE GAN they can generate images with higher diversity.
Chelsea, can I just interrupt for
Yes.
1 second? You're
Sure.
getting close to your time. I know this is really complex work to describe.
Yeah, I will
but
be quick. Thank you for reminding. Yeah. And in addition to the quality test, we also conducted diversity tests. We use a maximum mean distribution M.I.T. It also calculates difference between the feature means of the two data sets. So usually a higher distance indicates the line similarity and a higher diversity. So let's look at this figure. So we use two different like linear kernel and the polynomial kernel to compare the style GAN and DD GAN. So in both different way of the comparison, we can see DD GAN have a higher M.I.T. compared with the style GAN. So this states that DD GAN model performs well in generating with less similarity to the original data set, and also the generated samples with more diversity. And lastly, we want to test the desirability of the generated samples by using the DD GAN. The desirability here means how people like the products or how the products performs in terms of the reviewer's perspective. So we use our well-trained DD model, which is the evaluation model, to predict the sentiment value of the product in terms of the reviewer's rating score. So the desirability is like represented in terms of like several attribute and the overall like performance. So as you can see, we have like two different results for style GAN and DD GAN. So these values represents the rating scores the performance rating that's user like give to the products based on the images of products. And also we can see the desirability of samples generated by DD GAN. They have like more than 9 to 56% increase compared with style GAN. And also by doing statistical analysis, we noticed that there are a lot of attributes such as attractionship until and in terms of time, I will not see them like specifically, but most of the attributes, they have significant improvements on the samples generated by DD GAN compared with style GAN. So we can see that DD GAN model, they can generate samples with higher user satisfaction compared with our baseline model, which is style GAN here. Okay, so yeah, this is a qualitative and a quantitative results of the evaluation on the performance of DD GAN. So we can conclude that DD GAN model, since it includes like data-driven design evaluation model, which is DD model, in the conventional GAN model, and this loss can like can send the feedback or send the user rating back to the generator, and the generator can adjust their generating process by leveraging this information. So we see the DD GAN model encourages the generator to generate more creative and more unfamiliar, and also potentially more novel samples. So this is about our work, and this only just start of the generative design in this domain. We still have a long way to go. So in the future, we are going to build a model that can generate a design concept based on maybe on the individual user, because in this work, we base on the whole large data set together and we average them, not on the specific one. So in the future, we will do the more customized generative design, and also maybe consider extreme users to broaden our novelty and diversity of the generative samples. And also,
okay, Chelsea, can I cut us here? Is this
sure.
Is this okay? Is this your last slide?
Yeah, that's also, yeah, that's the last point. So it's okay to end here.
Okay, wonderful. Thank you. So Almudena received her graduate degree in industrial design engineering from the Universitat de Cadiz, Puerto Real, Spain in 2018, and her master's degree in industrial design from the Universitat Politècnica de València, also in Spain, in 2020. She's now working as a pre-doctoral researcher with the Human Tech team under an FPU fellowship by the Spanish Ministry of Education and Vocational Training For research interests focused on industrial design and product evaluation, virtual reality and mixed reality technologies, and its influence in product perception. So she'll be presenting the paper, The Influence of Hand Tracking and Haptic Feedback for Virtual Prototype Evaluation in the Product Design Process. Almudena, I'll leave it to you.
Okay, thank you so much for the introduction. I'm going to share my screen. So are you able to see it?
Yes, it looks good, full screen. There you go.
Okay, well, so thank you so much for giving us the opportunity to share this work. My name is Almudena Palacios-Ibáñez, and I'm one of the authors of the research titled The Influence of Hand Tracking and Haptic Feedback for Virtual Prototype Evaluation in the Product Design Process, which is the research that I'm going to be presenting today. So this is the table of contents. I would like to first start with an introduction to the main topic of the research. Then I will talk about the main goals, followed by the materials and methods. And I will briefly explain the methodology followed, and I will end with the main results and conclusions of this investigation. So, well, conceptual design is a very important stage in the product development process. It's a critical phase because, as you can see in this graph, most of the design cost and the product cost are determined in this stage. On the other hand, many researchers agree that the success of a product is highly dependent on the evaluation process, which is mainly done in this stage. So, and given this context, physical prototyping is one of the most common methods to obtain user feedback. But traditional techniques may involve large financial and time investments in many cases, and that can be reduced by the use of virtual prototyping. So advances in technology have led to the emergence of new visualization techniques, such as virtual reality. So the use of virtual reality has proven to be an effective alternative for product evaluation, for the physical product evaluation. But its value is predicated on the assumption that the emotional and perceptual response that we have toward the product is similar to the one elicited by the real one, which is not necessarily the case. So, well, these advances have brought hardware improvements, so we are able to use new tools such as non-intrusive real-time hand tracking. But we realized that little research utilized this tool in the virtual environment to incorporate tactile feedback and reduce some of the perceptual differences that arise due to the presentation medium. So, well, we postulated 5 hypotheses. The first one is related to the evaluation process that takes place when we purchase a product. So it is that the purchasing decision is not affected by the change of medium. Then we postulated that the visual medium used to present a product influences the user perception of the semantic scales, regardless of the classification in Jordan's category. So I will explain later some of the terms here for a better understanding. The third hypothesis was that the level of confidence in the response could be also affected by the change of visual medium. Then the user expertise and design background could affect product evaluation. And this hypothesis was postulated because little research studied this factor during product evaluation in virtual environments. And then finally, the use of a complementary item, which is something that I'm going to be explaining later again, and to assess a product influences the evaluation of the product semantic scales. So in this slide, you can see the methodology that we followed for the experiment. We designed 2 case studies. So A1 was a study of user perception of the product and design expertise. And for that, we use a real setting, a virtual reality setting, and the virtual reality with passive haptic setting. And for the second case study, that was an examination of the perceptual differences in product evaluation elicited by a complementary item. So because of some technical restrictions, we just use the real setting and the virtual reality setting. So 91 users participated in both case studies. And well, we used the MetaQuest 2 head-mounted display for both experiments. The virtual environment was designed using Unity. The interaction with the virtual environment was done using the Oculus integration asset, and the hand tracking interaction with the environment was designed using the HPCK posing and snapping asset. That was because at the time that we performed the experiment, the Meta interaction SDK was not available. So now I'm gonna talk a little bit about these concepts, the semantic differential and Jordan's pleasure categories. So for product evaluation, we use the semantic differential technique, which has been widely used on this kind of experiments. So it is composed by different bipolar pairs of adjectives. In our case, we use 12 adjectives as product descriptors. And to obtain more robust results, we classified them using the Jordan's pleasure categories. So this is an emotional approach proposed by Jordan. So he proposed 4 categories, which is the first one is the physio-pleasure category, which is the one related to the 5 senses. The psycho-pleasure category, which is related to how the product works. Then we have the sociological pleasure category related to product aesthetics. And the last one, which is the ideal pleasure category, which is related to people's values. So here you can see in this table, those 12 bipolar pairs of adjectives that we use for the product evaluation. So we selected 3 different designs of an umbrella stand as the main stimuli because of 3 main reasons. The first one is because it is an easy to use product, so we wanted to avoid some frustration. The second one, because the geometry guaranteed a good hand tracking experience. And the third one, because the use of a complementary item was needed. So the complementary item in this case is the umbrella. You need an umbrella to use this product. In this picture, you can see the physical rooms that we built for both case studies. So they consisted on 7 panels positioned contiguously and attached to this white wall. So in one of them, we displayed the virtual reality setting. So it was an empty room. And in the other, we displayed the real setting and the virtual reality with passive haptics setting. So the real prototypes of the products were available inside that room. Here you can see some pictures of the experiment. The one on the left is the virtual reality setting of the second analysis. So one user is trying to use the umbrella stand with the umbrella using the hand tracking. Here, well, this is just a picture about the setup of the experiment. And here you can see the virtual reality with passive haptics setting. So you can see one participant wearing the MetaQuest 2. And well, she's able to touch the real product while she's seeing the virtual prototype of this product too in the virtual environment. So I'm going to talk now about the results. But first, I would like to show you this scheme to let you know how we perform the statistical analysis for both case studies. So for A1, we obtained 3 different data sets. The first one was the semantic scales, the confidence in the response, and then the purchase decision. So for the semantic scales, well, we calculated the descriptive statistics, and we also performed 2-factor mixed ANOVA. And later we also perform post hoc tests just to know between which visualization technique the differences arise. For the confidence in the response and the purchasing decision, we apply the Q of Cochrane test, and we also perform pairwise comparisons. Finally, for the case study A2, we obtained the descriptive statistics for the semantic scales, and we also performed the two-factor mixed ANOVA. So, well, the first hypothesis was rejected. The statistical analysis results showed no differences between the visual media used. So our results agree with other authors. Well, the confidence in the response for this data set was high for each medium, which suggested that user had enough information to make a purchase decision, which may explain these results. This hypothesis was accepted. The visualization medium is to present the product influenced user perception of the semantic scales, but not all semantic scales were influenced in the same manner. So as you can see here, the umbrella stand B didn't show differences between the visualization techniques used. Umbrella stand C, sorry, show differences for simple and complex, and also for impractical, practical, and then the design A show differences for decorative and function. We also accepted this hypothesis as the statistical analysis showed differences for the visualization techniques. So the physio-pleasure category was the most affected. So it was related to the 5 senses. So this suggests that that category is one of the most difficult categories to evaluate in virtual environments. So here we also observed that the virtual reality setting obtained the lowest results, and that was because of the absence of haptic feedback. The statistical analysis also showed differences because of the design background. So that's why we accepted this hypothesis too. And finally, the use of the complementary item also influenced the evaluation of the product semantic scales. So here you can see the main conclusions of this research. The visual medium used to present a product could influence how it is perceived. So not all pleasure categories in Jordan's classification were influenced equally by the visual medium, and differences in the semantic scales between visual media were due to the absence of the sense of touch during the visual experience. And finally, the individual's background does not influence the confidence in the response, but it can influence the assessment of certain product features, particularly in the physiological and the ideological pleasure categories. So our work contributes to the area of product design by empirically assessing the reliability of virtual reality and virtual reality with passive haptics as a tool for product evaluation in the early stages of the product development. And well, this is everything. So thank you. And if you have any question, I would be happy to respond.
Thank you